Let's get a quick example of this by just investigating what a field looks like. So here's a velocity field. We don't know where this came from yet, but it's given by this equation that says we've got v0 over L, which is just some constant number, some constant, multiplied by the position vector minus x I hat plus y j hat. And so this is some velocity field. You could plug in any value of x and y, and out would come a value of velocity, but it would be a vector, right? We'd have an I component and a j component. Well, the question's asking us to find locations where the velocity magnitude, this is just the magnitude of velocity, is equal to some value v0. So whatever this number here is, we just want to find out where that is. So this is just a quick algebra trick here. All we need to do is take that velocity vector field that they've given us and compute its magnitude. And so the way you take a magnitude of a vector is that we take the components and we square them, add them together, and take the square root. So what are the components? Well, we can multiply this out real quick and discover that the x component, u, is equal to minus v0 over L times the position x. And the y component in the j direction here, we'll call that velocity v, is equal to v0 over L times y. So let's drop those into our magnitude calculation here. And so we're going to have minus v0 over L times x. We're going to square that whole quantity, and we're going to add to it v0 over Ly. Square that whole quantity, and then magnitude is the square root of that. And so a little bit of manipulation will show that this is equal to magnitude v0 over L, that part factored out, and we're left with x squared plus y squared, sorry that's just sloppy, there we go, to the 1/2, which you may recognize. This is the equation parametric for a circle, and we've got this value here. And so what we can say then, whoops, got that off a little bit, there we go, straighten that out. Pardon me, I'll get better at this. What we can say then is that the velocity is equal to v0 anywhere that this is equal to 1. Anywhere that x squared plus y squared 1/2 over L is equal to 1. Right, we just want this equal to 1, or to v0, and the only time that's going to happen is when all of this business attached to it, all of this stuff here, just has to be equal to 1. And so we can solve that directly. So that's kind of interesting. Why is that useful? Well, let's draw a picture of it and find out real quick. So there's the answer we were looking for, but let's just plot it. So if we take this field and we put it on a coordinate, I'm not going to do all of it, but we'll do, say, the right side here. We can call this x and this y. If you start putting in values for x and y, we can get some vectors. And so just applying the original velocity field, we end up out in this region where x and y both have values. We get something that looks like that. But as we get closer down, remember the equation for this line, or for this field, has y and x in it. So as you get a smaller y value, that means that the horizontal component becomes dominant and the vertical component is very small. They're proportional. So as we get close down to the axis, you're going to get things that look more like this. In fact, along the axis, you see values where there is no vertical component, and as x shrinks, so does the velocity magnitude in that direction. The punchline of all this is that you can do the same in the y direction. Here x is tiny and y is big, so that means that u is tiny, v is big. And as you work your way down, what you're going to discover is that this is the velocity field for essentially blowing against a wall. Now we don't know how to obtain that yet, but we will. And what we're looking for are places where x squared plus y squared over L is equal to 1. And so you could solve that and you discover, say, that maybe this point here has a value v equals to v0 magnitude-wise, and so on. And so that's kind of the interesting idea of this problem.